Every time your email sends a message straight to the spam folder, or like an AI language model drafts just this flawless response to your prompt, those systems are secretly relying on an essay that sat completely ignored in the desk drawer of an 18th century clergyman.
Yeah, literally just gathering dust.
Exactly. So today, you and I are diving into an incredibly insightful tech blog post by Aaron Rose, and it's titled Thomas Bayes and the Theorem in the Drawer.
It's such a great read.
It really is. Rose frames this massive technological history through this brilliant lens. We follow a conversation between two engineers, a senior software engineer named Margaret and her junior colleague Timothy.
Right, as they sit together in this, grand Victorian library in London.
Yeah, the setting is perfect. And through their dialogue, we explore how an unpublished paper left behind by a quiet minister fundamentally changes not just artificial intelligence, but how you and every human being on Earth should go about making decisions.
It's huge.
Okay, let's unpack this, because to understand the future of technology, we really have to start with a man who actively avoided the spotlight.
We really are looking at a profound study in contrasts here. I mean, the source text introduces us to Thomas Bayes, who was born in 1702 and lived until 1761.
Right.
And Margaret explains to Timothy in that Victorian library that Bayes was a nonconformist minister in Tunbridge Wells. He was this incredibly quiet, scholarly man who just spent his days doing, ordinary clergyman things.
Like tending to his congregation and reading.
Exactly, reading and just thinking deeply about the world around him.
And crucially, he kept those thoughts to himself. I mean, he published almost nothing during his entire lifetime.
Yeah, only 2 works, I think.
Just 2. And one of those was published anonymously.
Which just tells us so much about his temperament, right? He was observing how humans form beliefs and how we struggle with uncertainty.
Oh, we definitely struggle with it.
For sure. But he was incredibly cautious about declaring he had the definitive answers. So he quietly searched for a better, more rigorous way to reason through the whole messiness of human judgment.
And then he worked out his solution, wrote it down on a piece of paper, and then simply left it in his desk.
Which is wild to think about.
The irony there is almost too heavy to lift. I mean, we live in this hyper-connected information age where people broadcast every half-baked thought they have on the internet.
Oh, totally. Every single one.
Yet the actual mathematical backbone of our entire era, the engine powering algorithms and massive data sorting, it came from a man who practically refused to share his own revolutionary ideas.
Well, he literally took it to his grave. He died in 1761, completely unaware of what he had accomplished.
Wow.
Yeah, it wasn't until a friend of his, Richard Price, went through his papers after the funeral that this essay was even discovered.
So Price just stumbled upon it.
Pretty much. Price recognized the brilliance of the math, edited the manuscript, and sent it to the Royal Society in 1763, which was 2 years after Bayes passed away.
So this theorem, sitting in the dark, gets pulled out of a drawer and sent to the most prestigious scientific body in the world.
Yeah, the Royal Society.
But what actually was it?
Yeah.
Because the question Bayes was trying to answer wasn't just about, rolling dice or pulling cards from a deck. It was a massive philosophical shift.
A total paradigm shift.
Margaret lays it out for Timothy as they sit in the library. She says the core question Bayes answered was, when you learn something new, how much should you change your mind?
What's fascinating here is how violently classical statisticians rejected that premise.
Really? Violently?
Oh, yeah, because before Bayes, the dominant view of probability was entirely what we call frequentist. It was strictly objective.
Like just counting things.
Exactly. Probability was just counting. If you flip a coin 1,000 times and you get 500 heads, that observable frequency is your probability.
Got it.
The frequentist mindset argued that probability is a physical property of the universe. It's something you measure by repeating an event over and over.
Wait, I'm going to play the skeptic here for a second, because I totally understand why a classic mathematician would reject Bayes.
Okay, let's hear it.
Well, isn't mathematics supposed to be entirely objective? By definition, a degree of belief is subjective. It's a personal feeling.
Right.
So if I just plug my personal gut feeling into a mathematical equation, that sounds like a recipe for total bias. How does that actually work without the whole scientific method just falling apart?
And that tension right there is the crux of the entire Bayesian revolution. Statisticians push back for 200 years for the exact reason you just gave.
So my skepticism is historically accurate.
Totally. They accused Bayes of smuggling subjective opinion into the pure realm of mathematics. But Bayes wasn't suggesting we just use our feelings.
Okay.
He invented a highly constrained, rigorous mechanism to prevent human bias and ensure that your belief updating is mathematically locked to reality.
Locked to reality. I like that.
He built an engine with 3 moving parts, basically: prior, evidence, and posterior.
The prior, the evidence, and the posterior.
Right. So let's break down how that engine runs using a brilliant example Margaret gives in the article.
Yeah, the picnic one, right?
Yes. Imagine it's Wednesday, and you are planning a massive outdoor picnic for this coming Saturday. Before you look at any weather forecast, you already hold a baseline belief about the weather.
Just based on where I live.
Exactly. Based entirely on the time of year and where you live, you know there is roughly a 20% base chance of ruined picnic-level rain on any given Saturday.
Okay, so that 20% is my prior. It is the baseline probability before any new information enters the picture.
Now, fast forward to Friday evening. You step outside, look up, and the sky is heavy and completely overcast.
Oh.
Right. This is your evidence.
Yep.
You happen to know from historical weather data that when heavy rain actually does arrive on a Saturday, an overcast Friday evening preceded it about 80% of the time.
Let me stop you there, because my immediate human instinct is to completely panic. If 80% of rainy Saturdays start with a cloudy Friday, and I'm looking at a cloudy Friday, my brain jumps to the conclusion that my picnic is doomed. Like, I'm ready to cancel the caterer right now.
Which is the exact human flaw Bayes was trying to fix.
Ouch. Okay.
You are isolating one piece of evidence and forgetting the broader context. You also have to consider the false alarm rate.
The false alarm rate.
Yeah, you know that passing weather fronts happen all the time. In fact, roughly 30% of completely dry Saturdays also follow a cloudy Friday.
Ah, okay. So the cloudy sky shifts the picture, but the high false alarm rate dilutes that heavy 80% correlation.
Precisely. Instead of guessing how much to panic, Bayes' theorem forces you to run the numbers.
You actually plug it in.
Right. You plug your 20% prior into the formula, weigh it against the evidence of the clouds, and account for that 30% false alarm rate.
And then the engine churns.
The math engine churns, and it spits out your posterior, which is your new, rigorously updated belief. Because that false alarm rate is so high, it pulls your probability up from the 20% baseline, but it anchors it at roughly a 45% chance of rain.
Man, that is such a crucial distinction. It mathematically doubles my expectation of rain based on real evidence, but it acts as a speed bump against my own panic.
Exactly. It keeps you grounded.
It stops me from jumping to absolute certainty. I'm updating my belief, but only in exact proportion to the weight of the evidence.
And the brilliance of the system is that it loops.
Oops, how so?
That posterior, the 45%, it doesn't just sit there. It immediately becomes your new prior for whatever happens next.
Oh, wow.
Yeah. If you wake up Saturday morning and hear thunder in the distance, you don't start over. You take that 45% prior, feed the thunder in as new evidence, and generate a new posterior. The belief constantly refines itself.
It's essentially the mathematical version of being a detective walking into a crime scene.
Oh, that's a good way to look at it.
Yeah, like you never walk into a room totally blind, guessing at random. You start with a prior, maybe a suspect list, based on the victim's known associates.
Right.
Then you find a muddy footprint by the window. That's your evidence. You don't immediately arrest the person with big boots. Instead, that footprint systematically shifts the probability of who on your list did it, giving you a posterior suspect board.
A posterior suspect board. I love that.
And then you find a broken watch. You take the new board, apply the new clue, and update again. You are zeroing in on the truth, one clue at a time.
If we connect this to the bigger picture, Bayes originally mapped out this exact backward reasoning logic using a thought experiment about a billiard table.
Wait, a billiard table?
Yes, and it perfectly illustrates the detective metaphor you just used. Imagine throwing a billiard ball onto a large table that is hidden behind a heavy curtain.
So I can't see the table at all.
Exactly. You have absolutely no idea where it stopped. That vague uncertainty is your prior. Then you throw a second ball blindly behind the curtain. You hear a loud clack as it hits the first ball, and then you watch the second ball roll back out from under the curtain on the far left side.
Okay, so seeing where the second ball emerges is my evidence.
Exactly. You still can't see the first ball. But based on where the second ball bounced out, you can intuitively update the probability of where the first ball is hiding.
And then you just keep throwing balls.
Right. You throw a third ball, hear another clack, see another bounce, and you update your belief again. Bayes realized we spend our entire lives reasoning backwards from effects to causes.
Which is so true.
We are inferring what we cannot see based on a systematic observation of the clues we can see.
Here's where it gets really interesting, though. If this mathematical engine is so elegant, and if it maps so perfectly onto how we navigate the world, why didn't it take over mathematics immediately?
That's a great question.
Like, why did it sit in the dark for 2 centuries? Because from 1763 until the middle of the 20th century, almost no one was actually using Bayes' theorem to solve complex problems.
The barrier was purely technological.
Oh, really?
Yeah, conceptually, Bayes' theorem is a masterpiece, but computationally it is an absolute nightmare.
The math was just too heavy.
Completely intractable for the tools of the time. Think about updating the probability of a single weather event or a single billiard ball.
Okay, pretty simple.
Right. Now imagine trying to update the probability of a complex system with hundreds of overlapping variables, where every single variable affects the prior of every other variable.
My head hurts just thinking about it.
Exactly.
Hmm.
Doing those calculations by hand with a quill and parchment, or even with early mechanical calculators, it would take lifetimes. It was physically impossible to run the Bayesian engine at scale.
So Bayes essentially wrote an algorithm for a machine that wouldn't be invented for another 250 years.
Yeah, pretty much.
The concept was waiting for the physical infrastructure of the world to catch up.
That's the tragic reality of his timeline. The Bayesian revolution had to wait for the invention of fast electronic computers.
But even early computers struggled, right?
Yes, even they struggled with the sheer volume of calculations required. The source highlights a massive breakthrough that finally unleashed Bayes' theorem, which was the development of Markov chain Monte Carlo methods.
Markov chain Monte Carlo. That sounds incredibly dense.
It is a bit of a mouthful.
How did that actually solve the bottleneck?
Think about it this way. If you wanted to predict the weather using strict brute force Bayesian math, the computer would try to calculate the probability of almost every single possible drop of rain in the atmosphere.
That would just fry the circuits of even a modern machine.
Exactly. The Monte Carlo method offered a brilliant shortcut. Instead of calculating every single possibility, it takes clever, randomized samples of the data.
Like polling a population?
Sort of. By taking enough random samples and seeing where they tend to cluster, the computer can get an incredibly accurate estimate of the posterior probability without having to do the exhaustive, impossible math.
Oh, wow.
It was a workaround that saved massive amounts of computing power.
Because computers and these sampling shortcuts finally solved that massive math problem, Bayes' theorem broke out of the academic laboratory and crashed straight into our daily lives.
It's everywhere now.
It really is. As Margaret tells Timothy in the library, once you know what to look for, you realize this 18th century engine is humming silently all around you. Starting with something you probably checked 10 times today, your email inbox.
Oh yeah, spam filters are one of the most famous early applications of Bayesian logic.
I rely on mine heavily.
We all do. Your email provider doesn't just block a list of bad words. It uses a descendant of Bayes' theorem to actively protect your inbox.
How does it do that?
It starts with a base prior probability of any incoming email being spam. Then it looks at the evidence. Does the email contain the word lottery? Does it use excessive exclamation points?
Is the sender totally unknown?
Right. The system weighs each of those features as evidence, continuously updating the posterior probability. If the final number crosses a certain threshold, the email vanishes into your spam folder.
It's reading the clues and updating its belief about the email. And the article points out this scales up to the most advanced technology we have today.
It really does.
The AI language models that are currently revolutionizing every industry are fundamentally operating on this exact principle.
They are essentially massive Bayesian engines. When you give an AI a prompt, it doesn't think in English.
Right.
It maintains a sprawling probability distribution of what the very next word should be. It looks at the words you typed, and that's the prior context.
Okay.
It predicts a word, looks at that new word as evidence, and updates its distribution for the following word. It is cycling through the prior, evidence posterior loop thousands of times per sentence to construct human-sounding language.
It's dropping the billiard ball behind the curtain thousands of times a second to see where it counts.
That is exactly what it's doing, and it extends beyond text generation into critical fields like medical diagnosis.
Oh, right.
Modern diagnostic AI systems are explicitly Bayesian. They start with a prior, which is the baseline rate of a specific disease occurring in the general population.
Okay, so the base chance of having the disease.
Then a patient walks in and presents symptoms. A fever is a piece of evidence. A cough is another piece. The AI updates the probability of different diseases with each new symptom.
Zeroing in on the cause.
Exactly. A world-class diagnostic tool is just performing highly complex Bayesian reasoning to zero in on the correct illness, balancing the rarity of the disease against the specific clues in the patient's chart.
So what does this all mean for you and me?
That's the big question.
Right. I mean, we don't have supercomputers in our heads, and we can't run Monte Carlo simulations to decide what to eat for breakfast.
Thankfully.
Yeah. How do we take this centuries-old mathematical engine and actually apply it to our own personal growth?
The core lesson Margaret imparts to Timothy is about intellectual humility. You never start from scratch. You already hold beliefs about the world, your career, your relationships.
You always have a prior.
Yes. When new evidence arrives in your life, your responsibility is to update what you believe in exact proportion to what that evidence dictates. No more and no less.
Which means we have to actively avoid two massive traps of human psychology.
Right.
The first trap is ignoring our prior entirely. This happens when we treat every single new data point in total isolation.
We have all been guilty of this.
Totally. You get one piece of harsh feedback from a boss, and suddenly you convince yourself your entire career is a failure and you are going to be fired.
Panic sets in.
Yeah. You completely ignored your prior, which is the 5-year track record you have of doing excellent, heavily praised work.
The prior is your anchor. It keeps the heavy winds of sudden evidence from blowing you off course.
Right.
But the second trap is equally dangerous, refusing to update at all.
Stubbornness.
This is the definition of stubbornness. It is holding on to your original prior belief, regardless of how much contradictory evidence is piling up right in front of your eyes.
Even when the footprints are right there.
Exactly. Bayes isn't asking you to constantly flip-flop your opinions with every passing breeze. He is demanding that you change your mind systematically and honestly when the weight of the evidence finally requires it.
We have to be willing to do the math on our own egos.
This raises an important question, and it is the thought Margaret shares as they sit surrounded by all those old books in the Victorian library.
What's that?
Well, Timothy wonders what Thomas Bayes would have thought about all of this. Spam filters, AI language models, medical diagnostics. Margaret suspects he would have found it completely natural that machines use his logic today.
Because he spent his entire life watching humans fail to use it.
Precisely.
He was a minister. He watched his congregation struggle with uncertainty, watched them panic over single events, and watched them stubbornly cling to false beliefs.
He saw it every week.
He didn't build this rule set because humans are naturally good at updating their beliefs. He built it because we are terribly fundamentally flawed at it.
He created a perfect system for a deeply imperfect species.
Which leaves us with a truly fascinating philosophical angle to consider. We marvel at the fact that machines are using Bayes' theorem to achieve artificial intelligence.
It's incredible.
But maybe the real revelation here isn't about artificial intelligence at all. Maybe Bayes' theorem is actually the mathematical formula for human wisdom.
Oh, I love that.
If the core of the theorem is the systematic willingness to let your prior be rewritten by the truth of the evidence, then perhaps wisdom is just the courage to let your mind be changed.
That's a powerful thought.
It makes you wonder, when you encounter a piece of evidence today that challenges something you deeply believe, are you going to stubbornly defend your prior, or are you going to run the engine and let yourself learn?